Almost everyone carries the same quiet assumption about infinity. They think it is just a number that got out of hand. A very, very large amount, the biggest thing there could ever be. But here is what they were never told. Infinity is not one thing. It is not the biggest of anything, and it does not obey a single rule you would recognize. There is a size of infinity, and then a strictly larger size, and then a larger one still, rising in a tower with no top. You can cut one of these infinities exactly in half and find that nothing was lost. You can prove, with the same certainty as 2 plus 2, that most of the numbers on a simple ruler are numbers no human will ever name. The terrifying part is not that infinity is chaos. The terrifying part is that infinity has laws, and they are not your laws. So get comfortable. Hit subscribe if you're new here, because by the end of this, the word infinity will never sound like just a big number again. Now, let's slowly ease into this. Part 1. The game that opens a trapdoor. There is a game you already know how to play, even if no one ever told you it was a game. Write down the numbers from 1 to 10. Now go through them and quietly remove every odd one. Cross out the 1, the 3, the 5, the 7, the 9. Look at what is left. 2, 4, 6, 8, 10. 5 numbers, where a moment ago there were 10. Exactly half of what you started with. Nothing surprising has happened yet. You took a handful of numbers, you threw half of them away, and half remained. This is the most ordinary arithmetic in the world, the kind of thing you could teach a child in an afternoon. So, let us make it slightly bigger and see if anything changes. Write down the numbers from 1 all the way to 100. Then do the same thing. Find every odd number and take it away. When the dust settles, you are holding 50 even numbers, and you threw 50 odd numbers into the bin. Again, exactly half. The pattern is steady, reassuring, and completely unremarkable. Whatever size you start with, you remove the odds, and you are left with half as many as before. You could keep doing this forever, and the rule would never break. Take any pile of counting numbers, cut away the odd ones, and you reduce it to half its former size. Tonight, though, I want to do something that sounds harmless and turns out to be anything but. I want to ask what happens if you do not stop. Imagine, instead of stopping at 10 or at 100, that you write down all of the counting numbers, every single one, 1, 2, 3, 4, and onward, an endless line of numbers marching off into the dark with no final number anywhere in sight. Now reach into that infinite line and remove every odd number exactly as you did before. Take away the 1, the 3, the 5, the 7, on and on forever, until only the even numbers remain. You are left with 2, 4, 6, 8, 10, 12, and so on without end. And here is the question I want you to sit with, because it is the seed of everything that follows. Are there now fewer even numbers than there were counting numbers to begin with? Your instinct will answer before you can stop it. Of course, there are fewer. You just removed half of them. You took an infinite line and you struck out every second member of it. Half of everything is gone. How could what remains possibly be as large as what you started with? It feels less like a question and more like an insult to common sense. The whole was the full line of counting numbers. The evens are only a part of that line, a part you carved out by deletion. And surely, a part cannot be as big as the whole it was carved from. That single conviction, that the whole must be greater than the part, is one of the oldest and most trusted ideas a human mind can hold. You did not learn it in school. You were born understanding it. A slice of bread is smaller than the loaf. A handful of sand is less than the beach. Take anything, remove some of it, and what is left is smaller than before. And yet that puzzle, the question of whether an infinity can be cut clean in half and still somehow remain just as large as the whole, teased and tormented careful thinkers for centuries, not amateurs. Some of the finest minds in mathematics circled this question and backed away from it, because every time they tried to pin it down, it slipped between their fingers. There was no rigorous way to say what it even meant for one endless collection to be the same size as another. You cannot count an infinite line. You will never reach the end to compare your totals. So the words larger and smaller and equal, words that feel so solid when you are dealing with 10 numbers or 100, turn to vapor the moment you try to apply them to something that never ends. For most of human history, the safe response was simply to refuse the question. Do not speak of a completed infinity. Do not treat the endless line as a finished object you can hold in your hand and weigh against another. Talk only of going on, of processes that never stop, and never of the whole infinite thing as a single, real, examinable object. That was the wall, and almost everyone respected it. To step over it, to insist that the infinite could be treated as something real and measured and compared with the same cold precision you would use on the number 5, you needed a particular kind of mind, stubborn, a little reckless, willing to be told by the most powerful people in your field that you had lost your way and to keep walking anyway. It is worth dwelling for a moment on just how ancient and how trusted the rule really is, the one that this puzzle threatens, because that is the source of the unease. More than 2,000 years ago, the geometer Euclid laid down a short list of self-evident truths at the start of his great work on geometry, statements so obvious they could be assumed without proof, the bedrock on which everything else would be built. And one of them, one of these common notions as he called them, was simply this: the whole is greater than the part. Euclid did not argue for it. He did not need to. It was meant to be one of those things no sane person could doubt, in the same family as the statement that things equal to the same thing are equal to each other. For more than 20 centuries, it sat there, unquestioned, a piece of the furniture of every educated mind. You used it today without noticing, every time you judged that a slice was less than the cake, or that a chapter was shorter than the book, and that is exactly why the even numbers puzzle has teeth. It does not attack some obscure technical claim. It walks straight up to one of the oldest load-bearing beliefs in all of human reasoning and asks, very politely, whether it might be false. When you removed every odd number from the infinite line, you took away a part, an infinite part, and your whole life of experience insists that what remains must be diminished. The trouble is that nobody, for all those centuries, could actually prove it one way or the other for the infinite case, because there was no rigorous way to say what same size even meant when neither collection could ever be counted to the end. The question simply hung in the air, too slippery to grasp, too unsettling to ignore. People sensed that something strange lurked there, and they mostly chose to look away. It took exactly that kind of mind to give infinity a language of its own, to show, with proof rather than poetry, that our everyday notions of number do not merely bend when they reach the infinite, they shatter. And what is so unsettling about this story is not that infinity turns out to be vague or chaotic or beyond all understanding. It is the opposite. Infinity turns out to obey laws, strict ones, precise ones, laws you can write down and prove, laws as firm as any equation you ever met. The trouble is that those laws look nothing like the rules you have trusted your whole life. In the world of the infinite, you really can cut something exactly in half and have it remain exactly as large as it was before. You can take a part and discover it is the size of the whole. And once you have seen that happen, once you have watched a rule you thought was unbreakable simply fail in front of you, a small crack opens in your certainty about everything else. Because if that rule was wrong, you have to ask quietly what else you believe, only because you have never pushed it to the edge. So let us walk to that edge together. It begins, as so many dangerous ideas do, with a single person who would not leave a forbidden question alone. Part 2. The Man Who Refused the Rule. His name was Georg Cantor, and he was born on the 3rd of March, 1845, in the city of St. Petersburg, into a family with money and music running through it. His father was a successful merchant, a man of commerce and careful accounts. His mother came from a distinguished musical family, and the gift ran in the blood. Cantor himself was a serious musician, particularly on the violin, the kind of child who might have made a respectable life inside the warm, ordered world of concert halls and counting houses. When he was around 11, the family moved from Russia to Germany, and it was there that something else began to take hold of him, something that would never let go, a hunger for mathematics. Not the practical arithmetic of his father's ledgers, but the deep, strange, almost philosophical end of the subject, where the questions stop being about how much and start being about what is real. He studied in Berlin, which in those years was one of the great centers of mathematical thought on Earth, learning from some of the most formidable mathematicians of the age. He earned his doctorate in 1867, a young man with every reason to expect a brilliant conventional career. And then, 2 years later, in 1869, he took a position at the University of Halle, a smaller and less glamorous institution than the great schools of Berlin. He would remain at Halle for almost the whole of his working life. It was a quieter stage than his talent deserved, and everyone, including Cantor, knew it. But the modesty of the setting did not shrink his ambitions. If anything, it freed him. Tucked away in Halle, out of the brightest spotlight, he began to chase a question that more cautious and more celebrated men had learned to leave strictly alone. What does it actually mean to speak of infinity? You have to understand how dangerous that question was considered to be. For more than 2,000 years, infinity had not really belonged to mathematics at all. It belonged to philosophy and to theology, to arguments about God and eternity and the endlessness of the heavens. The great philosopher Aristotle had drawn a sharp and careful line, and that line had held for millennia. He was willing to accept what he called a potential infinity, by which he meant a process that can go on without ever stopping. Counting is like that. You can always add one more, so counting never has to end. Dividing a line is like that. You can always cut a piece in half again, those endless processes he allowed. But a completed infinity, an actual infinite totality existing all at once, the whole endless thing gathered together as a single finished object that he rejected outright. To Aristotle, and to almost everyone who came after him, the infinite was something you moved toward and never something you arrived at. This was not the prejudice of one ancient thinker. It ran straight through the heart of mathematics into Cantor's own century. One of the greatest mathematicians who ever lived, Carl Friedrich Gauss, a man whose name sits among the immortals of the field, wrote in a letter in 1831 that he protested, above all, against the use of an infinite quantity as something completed, which he said is never permissible in mathematics. The infinite, Gauss insisted, is only a manner of speaking. Read that again, because it tells you exactly what Cantor was up against. Not a fringe opinion, the settled judgment of the discipline's finest mind. The infinite is only a manner of speaking, a figure of speech, a convenient shorthand, useful, perhaps, but not a real thing you could ever lay on the table and study. Many of Cantor's contemporaries felt the same way, treating infinity as a kind of poetic gesture toward the very large, and resisting with real force any attempt to promote it into a genuine mathematical object with properties of its own. Cantor refused. That is the whole of it, and it is everything. He simply refused to accept those limits. He was prepared to treat infinity as something real, an actual infinite, that could be studied, handled, and compared with the same rigor and the same seriousness you would bring to ordinary numbers. Where Aristotle and Gauss saw a wall and a warning, Cantor saw a door, and he decided to walk through it and see what was on the other side. It was an act of intellectual nerve that is hard to overstate. He was, in effect, telling the assembled wisdom of 2,000 years that it had been too timid, that the thing everyone agreed could not be done was exactly the thing he intended to do. There is something else worth knowing about why this question gripped Cantor so completely, because it was not, for him, a dry technical exercise. Cantor was a deeply religious man, and he came to believe that the study of the actual infinite touched on something close to the divine. He drew a careful distinction in his own mind between the transfinite infinities he was discovering, the endless ladder of larger and larger sizes that still behaved like numbers and obeyed laws, and what he called the absolute infinite, which he associated with God, a true and final infinity beyond all the others and beyond all comprehension. For Cantor, mapping the transfinite was not an act of arrogance against the heavens. It was almost an act of reverence, a way of tracing the lower rungs of a ladder whose top belonged to the absolute. This is part of why he could withstand so much hostility for so long. He did not experience his infinities as a clever game he might be wrong about. He experienced them as a truth he had been permitted to glimpse, and that conviction gave him a kind of immovable stubbornness that ordinary professional caution could never have supplied. He had been trained, remember, by formidable people. In Berlin, he had learned from Karl Weierstrass, one of the great architects of rigor in mathematics, from Ernst Kummer, and from Leopold Kronecker, the very man who would later become his bitterest opponent. He had absorbed the highest standards of proof the era could offer. So when he began treating completed infinities as real objects, he was not doing it sloppily, the way a careless amateur might. He was bringing the full weight of the most rigorous training available to bear on the one subject that training had always told him to avoid. That combination, impeccable technique aimed at a forbidden target, is exactly what made his work so hard to dismiss and so threatening to those who wished to dismiss it. That conviction set him apart, and it would eventually cost him dearly. Among his teachers in Berlin had been a powerful and brilliant mathematician named Leopold Kronecker, a man of enormous influence in the German mathematical world. And Kronecker was, as it happened, one of the most determined opponents imaginable of precisely the kind of thing Cantor was beginning to do. Kronecker did not believe in Cantor's completed infinities. He thought them not just mistaken but dangerous, a corruption of the clean and solid foundations of mathematics. The two men were headed, slowly and inevitably, toward a collision that would shadow the rest of Cantor's life, and we will come back to it, because the cost of this story matters as much as its triumphs. But at this early stage, Cantor was not yet thinking about enemies or careers or the judgment of history. He was simply following his instincts, letting logic lead him step by careful step into territory that almost no one had dared to enter. And the first thing he needed, before he could compare one infinity to another, was a way to measure size that did not depend on counting at all. Because counting, as you are about to see, was never going to get him to the end of an endless line. Part 3. A way of counting without numbers. Think for a moment about what you actually do when you ask how many. When you want to know the size of a collection, your reflex is to count it. 1, 2, 3, 4, reciting the familiar numbers and attaching them one by one to the things in front of you until you run out of things, and the last number you said is your answer. It is so automatic that it feels like the only possible method. But Cantor saw that hidden underneath this everyday habit was a deeper and more powerful idea, one that did not need the numbers at all. Picture 2 bags. One is full of red balls, the other full of blue balls, and someone asks you whether the 2 bags hold the same number of balls. The obvious approach is to count. You pull the red balls out one at a time, saying 1, 2, 3, 4 to yourself, until the red bag is empty and you have your red total. Then you do the same with the blue balls. 1, 2, 3, 4, until you have your blue total. If the two totals match, the bags held the same number. Simple. But now imagine you could not count. Imagine you did not even know the names of the numbers, that words like 7 and 12 meant nothing to you. Could you still answer the question? Cantor's insight was that you could, easily, and that the method you would fall back on is actually more fundamental than counting itself. Here is what you would do. Reach into the red bag and pull out one red ball. Reach into the blue bag and pull out one blue ball. Set them down together as a pair. Then do it again, red and blue, another pair, and again, matching them up 2 by 2 without ever speaking a single number. Keep going until you cannot anymore. Now look at what happened at the end. If both bags ran empty at exactly the same moment, with every red ball sitting next to its own blue partner and nothing left over on either side, then you know, with complete certainty, that the bags held the same number of balls. You never counted. You never needed to. You only paired. And if it did not come out even, if you ran out of blue balls, while red ones were still waiting in the bag, then there were more red than blue, plainly, because some red balls could find no partner. If instead you exhausted the red balls and blue ones remained, there were more blue. The pairing tells you everything that counting would have told you, and it does so without ever leaning on the numbers as a crutch. Cantor took this humble idea, this business of matching things up one to one, and recognized it for what it truly was. The real meaning of sameness of size. There is an even homelier version of this that makes the point land. Imagine you are about to give a lecture in a large hall, and a great crowd has gathered, and you are worried there might not be enough seats for everyone. You could, in principle, count every seat in the hall, a long and tedious job, then count every person in the crowd, an even longer one, and compare your two numbers. But there is a far smarter way, and you already know it, because you have seen it happen 100 times. You simply open the doors and let everyone file in and sit down. If, when the shuffling stops, every person has found a seat and there are no people left standing and no seats left empty, then you know, without counting a single thing, that the number of people exactly equaled the number of seats. If people are left standing in the aisles, there were more people than seats. If empty seats remain scattered through the hall, there were more seats than people. The filling of the seats is a pairing, each person matched to one chair, and the leftover, on one side or the other, or neither, gives you your answer. These little scenes feel almost too simple to matter, and that is exactly why they matter so much. They capture the entire seed of Cantor's definition in a form a child could follow. Two collections are the same size. If you can set up a perfect pairing between their members, every element of one matched with exactly one element of the other, and nothing left unmatched on either side. What matters is never the reciting of numbers. It is the pairing. Cantor gave this perfect pairing a name we still use. He called it a one-to-one correspondence. When such a correspondence exists between two collections, we say they have the same size, or in the more formal language, the same cardinality. That word, cardinality, is just the careful term for the size of a collection. For a finite bag of things, it is simply the count, the cardinality of the collection containing the numbers 1, 2, and 3 is 3. The cardinality of the collection of vowels in English, A, E, I, O, U, is 5. Order does not matter, and if you accidentally list something twice, it still counts only once. It helps to see how deep this pairing idea really runs, how it sits underneath counting rather than beside it. Long before anyone had names for numbers, a shepherd needed to know whether the flock that came home at dusk was the same flock that went out at dawn. He could not count, not in the way we mean, because the words did not exist yet. But he could do something just as good. Each morning, as the sheep filed out, he dropped one pebble into a pouch for each animal. one pebble, one sheep, a perfect pairing. Each evening, as they returned, he took one pebble out for each sheep that passed. If the pouch emptied exactly as the last sheep came home, the flock was whole. If pebbles remained, a sheep was missing. He never knew how many sheep he had, in the sense of a number, and he did not need to. He had matched the sheep to the pebbles, 1 to 1, and the matching told him everything. That is Cantor's idea, thousands of years early, scratched out in stone and wool. And when you look closely at what we do when we count, even the modern way, you find the same pairing hiding inside it. To count a row of objects is to point at the first and say 1, the second and say 2, the third and say 3. What you are really doing is pairing each object with one of the counting numbers in order 1, 2, 3, until you run out of objects, and the last number you reach is the size. Counting is not something different from pairing. Counting is just a particular pairing, a matching of your objects against an initial stretch of the counting numbers. The numbers you recite out loud are simply convenient, standard labels, a reference collection everyone agrees on, so that two people who have each paired their things against the numbers can compare results without ever standing in the same room. Cantor saw straight through the labels to the matching underneath, and once you see it too, the leap to the infinite stops feeling like a trick. Now here is the quiet hinge on which the whole story turns. Cantor realized that this pairing test, unlike counting, does not care whether the collections are finite. Counting has to stop somewhere to give you an answer, and an endless collection never stops, so counting is useless on the infinite. But pairing has no such weakness. To check whether two infinite collections are the same size, you do not need to reach the end of either one. You only need to know whether a perfect one-to-one matching between them exists, whether every member of each can be partnered with exactly one member of the other, with nothing stranded. If such a pairing exists, the two infinite collections are the same size, full stop. They have the same cardinality. This is the key that unlocks the locked door. It is the tool that lets you do the impossible thing, the thing Aristotle and Gauss said could never be done. It lets you take two endless collections, two completed infinities, and ask with perfect rigor whether one is larger than the other. And the very first time Cantor turned this tool on the simplest infinity of all, it gave an answer that should have been impossible. So let us turn it there too, and watch a part become as large as the whole. Part 4. When the part becomes the whole. Start with the most obvious infinite collection there is, the one you have known since childhood, the natural counting numbers, 1, 2, 3, 4, 5, and onward forever. As every child eventually realizes, there is no largest number. If someone boasts that they can name the biggest number of all, you defeat them instantly by replying, just add 1. Whatever they said, you can go one higher and one higher than that, without end. The list of counting numbers goes on forever. This endless collection is going to be our reference, our home base, the infinity against which we measure all the others. So hold it firmly in your mind. The full, unbroken line of counting numbers stretching off into the dark. Now do to it the thing we did at the very beginning. Strip out all the odd numbers and keep only the evens. You are left with 2, 4, 6, 8, 10, and so on forever. These even numbers form what mathematicians call a proper subset of the counting numbers. That phrase simply means they are entirely contained within the counting numbers. Every even number is a counting number, but they do not make up the whole of them, because all the odd numbers have been left outside. The evens are a part. The full collection of counting numbers is the whole, and everything you know screams that the part must be smaller than the whole. For finite collections, that scream is correct, every time without exception. Take the first 5 square numbers, 1, 4, 9, 16, 25. That collection has 5 members. Now take a proper subset of it, say just 1, 4, and 9. That smaller collection has 3 members, fewer than 5, and it will always go this way. For any finite collection with some number of members, a proper subset, a piece carved out of it, must have fewer members than the original. It can never, ever match the size of the whole it came from. This is not a guess or a tendency. For the finite, it is an ironclad law, and it is the precise mathematical form of that deep human intuition that the whole is greater than the part. So our instinct, carried over from everything we have ever handled, insists that the even numbers, being only a part of the counting numbers, must form a smaller infinity. We expect there to be fewer evens than counting numbers. It feels not just true but obvious, the kind of thing only a fool would question. But Cantor's rule does not ask what feels obvious. It asks one question and one question only. Can you build a perfect pairing? And the answer, for the evens and the counting numbers, is yes, with humiliating ease. Watch. Take each counting number and match it to its double. 1 pairs with 2, 2 pairs with 4, 3 pairs with 6, 4 pairs with 8. In general, the counting number you might call n pairs, with the even number 2 times n. Now ask the only questions that matter. Does every counting number get a partner? Yes, of course, because you can double any number you like. Does every even number get used up as somebody's partner? Yes, because every even number is the double of exactly one counting number. Is anything left stranded on either side? Nothing at all. The matching is perfect, flawless, complete. Every counting number has exactly one even partner, and every even number is the partner of exactly one counting number. And so, by Cantor's definition, the only definition that survives contact with the infinite, the collection of even numbers, is precisely the same size as the collection of all counting numbers. The same cardinality. Read that slowly, because it is the moment the floor tilts. You took the full line of counting numbers. You deleted half of them, every odd one, an infinity of deletions. And what remained was exactly as large as what you started with. The part is the size of the whole. The oldest rule you know, the whole is greater than the part, simply does not hold here. It is not bent, it is not approximate, it is false. Infinity can be cut clean in half and remain, in the only rigorous sense there is, completely undiminished. If your mind is resisting, good. That resistance is the correct response, and Cantor's contemporaries felt it too. But once you accept the rule, the strangeness does not stop. It compounds. Let us thin the counting numbers out far more aggressively and see if we can finally make a smaller infinity. Take only the perfect squares. 1, 4, 9, 16, 25, 36, and so on. Each one made by taking a counting number and multiplying it by itself. Now the squares spread out fast. Between 1 and 4 there is a gap. Between 4 and 9 a larger gap. Between 9 and 16 larger still. And the gaps keep growing without limit as you go. The squares become rarer and rarer, lonelier and lonelier, scattered ever more thinly along the endless line. Surely, this desperately sparse collection is smaller than the full, densely packed counting numbers it was drawn from. Cantor says no, and the pairing that proves it is as simple as before. Match each counting number to its square. 1 pairs with 1, 2 pairs with 4, 3 pairs with 9, 4 pairs with 16. In general, n pairs with n times itself. Every counting number produces exactly one square, and every square comes from exactly one counting number. Nothing is left over. The pairing is perfect. And so the perfect squares, no matter how thinly they are scattered, are exactly as numerous as the counting numbers. The same cardinality again. I want to pause here, because this moment, the part turning out to equal the whole, is the true hinge of everything, and Cantor was not actually the first person to stumble onto it. More than 200 years earlier, around 1638, the great Galileo Galilei noticed exactly this strangeness about the squares. He saw that you could pair every counting number with its square, 1 with 1, 2 with 4, 3 with 9, so that there seemed to be just as many squares as counting numbers. And yet, he could also plainly see that the squares grow rarer and rarer, that most numbers are not squares at all, so there ought to be far fewer of them. Galileo, brilliant as he was, looked at this contradiction and concluded that the words equal, greater, and less simply do not apply to infinite quantities. He threw up his hands. The concepts break, he decided, so we should not use them in the infinite at all, and he walked away from the cliff edge. For 2 more centuries, that was the wisest available response, to acknowledge the paradox and then politely refuse to go further. What Cantor did, and what makes him the hero of this story, rather than Galileo, was to refuse that refusal. Where Galileo said the concepts of size break down for the infinite, Cantor said no, the concepts do not break down, our intuitions about them do. Size still means something perfectly precise for infinite collections. It means whether a one-to-one pairing exists. The trouble was never with the idea of size. It was with our smuggled-in assumption that the part must always be smaller than the whole, an assumption that is true for the finite and simply false for the infinite. Once you let go of that single false assumption, the paradox stops being a paradox and becomes a theorem. The squares are the same size as the counting numbers, calmly, provably, with no contradiction at all. Galileo found the trapdoor and stepped back from it. Cantor found the trapdoor, opened it, and climbed down to see what was underneath. And what was underneath was a world. Now let us try the opposite tactic. Instead of thinning the collection out, let us fatten it up and surely overflow our reference infinity. Take the counting numbers, then add 0, and then throw in all the negative whole numbers as well, -1, -2, -3, and so on. This larger collection is called the integers, and here your intuition has its strongest case yet. The counting numbers march off to infinity in one direction only. The integers march off to infinity in both directions at once, endlessly forward and endlessly backward. It seems beyond argument that a line running infinitely both ways must be bigger than a line running infinitely only one way. How could it not be? And yet, once more, the pairing defeats the intuition. List the counting numbers as your partners and walk through the integers in a zigzag. Pair 0 with 1, then step to the right and pair 1 with 2. Then jump to the left and pair -1 with 3. Step right again, 2 with 4. Jump left, -2 with 5. Keep zigzagging out from the center, alternating right and left forever. Every integer, positive, negative, or 0 eventually gets caught in the zigzag and handed a partner, and every counting number gets used exactly once. The pairing is perfect. The integers, running endlessly in both directions, are exactly the same size as the counting numbers running in only one. We have a name for every infinity that can be matched up 1-to-1 with the counting numbers in this way. We call it countable, or, in Cantor's own language, denumerable. The evens are countable. The squares are countable. The integers are countable. And each time, the part has matched the whole, and the ancient rule has lain there broken on the floor. But there was one collection so dense, so overwhelmingly crowded, that even Cantor's contemporaries were sure it must finally break the pattern. So let us go and meet the fractions. Part 5. The fractions that should have won. The fractions, the rational numbers, were supposed to be the collection that finally broke Cantor's pattern. We write them with the letter Q, and they consist of every number you can build as one whole number divided by another, any ratio of integers, A over B, where B is not 0, 1/2, 3/4, 17 over 5, minus 2/3, all of them. And notice, before we go further, that every integer is secretly a fraction too, because any whole number n can be written as n over 1, a perfectly good ratio. So the rationals already contain everything we have looked at so far, and then enormously more besides. To feel why the fractions seem certain to be a larger infinity, do not think about the whole endless line. Just think about the tiny stretch between 0 and 1. The counting numbers put nothing at all in that stretch. There is no counting number between 0 and 1. But the fractions crowd into it without limit. 1/2 is there, 1/3, 2/3, 1/4, 3/4. And it never stops, because here is the property that makes the rationals feel almost suffocatingly dense. Pick any two fractions, no matter how close together they sit, and you can always find another fraction squeezed between them. Just take their average, the point halfway between, and that is a fraction too, lying neatly in the gap. And then you can do it again, finding a fraction between those, and again, forever. Between any two rational numbers, however nearly they touch, lies an infinity of others. No matter how far you magnify the line, no matter how deep you zoom, the fractions are always there, packed in, dense beyond imagining. Set that against the counting numbers, which plod along in lonely, evenly spaced steps with vast empty deserts between them. 1, then a gap, then 2, then a gap, then 3. The contrast could not be sharper. On one side, a collection so thinly spread, it leaves enormous emptiness everywhere. On the other, a collection so dense, it fills every conceivable gap to overflowing. Surely, this time, the fractions form a larger infinity than the counting numbers. Cantor's own colleagues would have bet their careers on it, and Cantor said no. The rationals are countable. They can be matched 1 to 1 with the plain counting numbers, every fraction handed its own counting number partner with none left over. And the way he proved it is one of the most quietly beautiful pieces of reasoning in all of mathematics. He began with just the positive fractions, the ones of the form p over q, where p and q are counting numbers. And instead of trying to put them in order by size, which is hopeless, because between any two there are infinitely many more, he arranged them in a grid. Picture an endless table. Across the top, label the columns 1, 2, 3, 4, on and on. Down the side, label the rows 1, 2, 3, 4, on and on. Now into the cell that sits in column P and row Q, write the fraction P over Q, so the top left corner holds 1 over 1. Move right and you get 2 over 1, then 3 over 1, then 4 over 1, marching off forever across the top row. Drop to the second row and you get the fractions with a 2 underneath, 1 over 2, 2 over 2, 3 over 2, and so on. Fill the whole infinite grid this way, and here is the crucial thing. Every single positive fraction sits somewhere in that grid. Pick any fraction you like, and it has a definite home, a row, and a column where it waits. Now comes the move that turns this infinite grid into a single orderly list. You cannot just read along the top row, because that row by itself is already infinite, and you would never drop down to reach the others. So instead, Cantor traced a zigzag path through the grid along its diagonals. Start at 1 over 1, then sweep across to 2 over 1, then cut diagonally down to 1 over 2, then down again to 1 over 3, and back diagonally up through 2 over 2 to 3 over 1, then across to 4 over 1, and back down the diagonal, 3 over 2, 2 over 3, 1 over 4. Keep going, sweeping back and forth along ever longer diagonals, and the path will eventually reach every cell in the entire infinite grid. Nothing gets missed, because every fraction lives at some particular row and column, and the marching diagonals are guaranteed to arrive there sooner or later. This zigzag path strings all the positive fractions out into a single sequence, a first one, a second one, a third one, an orderly line. There is just one small housekeeping rule. As you walk the path, you will keep meeting fractions that are really just disguised copies of ones you already passed. 2 over 2 is just 1. 3 over 3 is just 1 again. 2 over 4 is just 1/2, which you already listed. Whenever the path lands on one of these duplicates, you simply skip it and walk on. With that single tidy rule, every positive fraction in its lowest terms appears exactly once in your sequence, with no repeats and no omissions. And now the finish is easy. Line up the counting numbers against this sequence. The counting number 1 labels the first fraction, 2 labels the second, 3 labels the third, and so on. Every fraction gets its own counting number label, and every counting number is used exactly once. To sweep in the negative fractions and 0 as well, you do the same trick we used for the integers, weaving positives and negatives together in alternation with 0 at the front. The result is a perfect one-to-one correspondence between the counting numbers and the entire collection of rational numbers. Let yourself feel the density for a moment, because it is genuinely vertiginous, and it is what makes the result so hard to accept. Pick a point on the line, any point, say 1/2. Now imagine zooming in on it, magnifying the line around it as if through an ever more powerful microscope. At first you see 1/2 sitting among its neighbours, 1/3 to the left, 2/3 to the right. Zoom in further, narrowing your view to a tiny window around 1/2, and the window does not empty out. It fills with more fractions, packed just as tightly as before. Zoom in 1,000-fold, 1,000,000-fold, 1,000,000,000-fold, and it never ever thins. At every magnification, no matter how extreme, you find infinitely many fractions crowding the view, because between any two of them, however close, there is always another, and another beyond counting. There is no scale at which the fractions become sparse. They are infinitely dense at every point, everywhere, all the way down. Holding that picture in your mind, the idea that this seething, bottomless crowd could be no more numerous than the lonely counting numbers feels almost like an insult to your senses. And yet the zigzag through the grid settles it beyond any argument. The crucial thing to understand is that the grid does not care about density at all. It does not arrange the fractions by where they sit on the line or how close they huddle together. It arranges them by their ingredients, by which whole number sits on top and which sits underneath. And those ingredients are just pairs of counting numbers which the diagonal sweep can march through one at a time forever. The density that overwhelms your eye is invisible to the grid. The grid sees only that each fraction is built from 2 counting numbers, and that pairs of counting numbers can be listed, and so the fractions can be listed, and so they are countable. Your intuition was measuring the wrong thing. It was measuring how crowded the fractions look on the line, when the only thing that determines their size as an infinity is whether they can be systematically matched against the counting numbers. They can. So the fractions, for all their dizzying density, for all the infinity of them crammed between any 2 points on the line, are countable. They are no more numerous than the simple counting numbers you learned as a toddler. And this is the deeper lesson Cantor is teaching us, blow by blow. The size of an infinite collection has nothing to do with how crowded it looks, or how much of the line it seems to cover, or how tightly its members are packed. Density is a trick of the eye. What matters, the only thing that matters, is whether you can build a systematic pairing with the counting numbers. For the fractions, dense as they are, you can, and so they fall into the same size as everything else we have seen. It is genuinely shocking. The rationals appear to swamp every inch of the number line, to be everywhere at once, and they turn out to be exactly as numerous as the lonely, widely spaced counting numbers. By now, you might reasonably conclude that this is just how infinity works. That every infinite collection, however vast it looks, is secretly countable, secretly the same size as the counting numbers, and that there is really only one infinity wearing many disguises. Cantor thought he should test that idea against the largest, richest collection of numbers he knew, and when he did, the ground did not tilt. It opened. Part 6. The number that cannot be on the list. The collection Cantor turned to was the real numbers, which we write with the letter R, and which is the most complete number line there is. You can think of the real numbers as every single point on the smooth, unbroken line, or equivalently, as every possible decimal expansion. Any number you can write with a decimal point, whether it stops after a few digits like 0.5, or runs on with a pattern, or runs on forever with no pattern at all, is a real number. The reals include everything we have already met. The counting numbers, the integers, the fractions, all sitting there on the line. But they also include a stranger and more numerous kind of number, the ones whose decimals go on forever without ever settling into a repeating pattern. Numbers like the square root of 2, numbers like pi, numbers like the constant e. These are called the irrational numbers because they cannot be written as any ratio of whole numbers, and their decimal expansions are endless and patternless. Put the fractions and the irrationals together, and you get the full real line, every point occupied, no gaps anywhere, stretching from the endless negative to the endless positive. So Cantor asked the natural question, the one his whole method had been building toward. The fractions, dense as they are, turned out to be countable. What about the reals? Can every real number be lined up, one to one, with the counting numbers? Or does this collection, finally, escape? To make the question manageable, he made a clever simplification. He did not try to handle the entire infinite line at once. He zoomed in on just the interval between 0 and 1, the reals with a decimal expansion beginning 0 point something. His reasoning was that if he could show even this single, modest stretch could not be put into a list, could not be matched with the counting numbers, then the whole real line, which contains this stretch and far more, certainly could not be either. Prove the small thing impossible, and the large thing is impossible for free. Then he did something audacious. He assumed the opposite of what he wanted to prove, and set out to wreck it from the inside. This is a method called proof by contradiction, and it is one of the sharpest weapons in mathematics. Suppose, Cantor said, that I am wrong. Suppose every real number between 0 and 1 can be written out in a single infinite list. A first number, a second number, a third number, and so on, with the promise that every real number in the interval appears somewhere on that list. I will take that assumption completely seriously, and then I will build, with my own hands, a real number between 0 and 1 that cannot possibly be anywhere on the list. If I can do that, the promise is broken, the assumption collapses, and the reals are proven uncountable. Here is how the construction goes, and it is worth slowing down for, because it is one of the most elegant ideas a human being has ever had. Imagine the list laid out in front of you. The first number is 0 point, then some endless string of digits. The second number is 0 point, then another endless string of digits. The third, the same, and so on down the page, each row a real number written as an infinite decimal. Now Cantor walks down the diagonal of this list. He looks at the first digit of the first number, then the second digit of the second number, then the third digit of the third number, the fourth digit of the fourth, marching diagonally down and across through the endless table of digits. And from these diagonal digits, he builds a brand new number, digit by digit, according to one simple rule. For the first digit of his new number, he picks something different from the first digit of the first number. For the second digit, he picks something different from the second digit of the second number. For the third digit, something different from the third digit of the third number. And he continues this way forever, always choosing his next digit to disagree with the digit sitting on the diagonal at that position. To avoid a small technical nuisance, the fact that a decimal ending in endless nines can equal one ending in zeros, he simply agrees never to use a 0 or a 9 in his construction, which changes nothing important. Now look at the number he has built, this 0 point, followed by his carefully chosen string of digits. Where could it possibly sit on the original list? It cannot be the first number, because he deliberately made its first digit different from the first number's first digit. It cannot be the second number, because its second digit was chosen to differ from the second number's second digit. It cannot be the third, the fourth, the millionth, or any number on the list at all, because at the corresponding position along the diagonal, his number was built to disagree. It differs from every single number on the list in at least one decimal place. And so this number, a perfectly legitimate real number between 0 and 1, appears nowhere on a list that was supposed to contain every real number between 0 and 1. The promise is broken. The contradiction is total. There is no escape from it. You might try to fix the problem by adding the new number to your list. But the moment you do, Cantor simply runs the diagonal trick again on your updated list and produces yet another number that is missing. No matter how you arrange the reals between 0 and 1, no matter how cleverly you order your infinite list, there will always be at least one real number left out. And if you can never make a complete list, then you can never set up the one-to-one correspondence with the counting numbers, because such a correspondence demands that every real number appear exactly once, with nothing omitted. The reals between 0 and 1 cannot be counted. And since that tiny interval already cannot be counted, the entire real line, vastly larger, cannot be counted either. In a single stroke, with nothing more than a diagonal and a refusal, Cantor had proven that the real numbers are uncountable. They form a strictly larger infinity than the counting numbers. There is more than one size of infinity. I want you to actually build that escaping number with me, slowly in your mind, because doing it yourself is the only way to feel why it is inescapable. Picture the list laid out before you, an endless tower of decimals, each one beginning 0 point and then trailing off into its own infinite string of digits. You are going to construct one new number, a single decimal, by walking down the staircase of the list. Step onto the first row and look only at its first digit, just after the decimal point. Whatever that digit is, you write down something different for the first digit of your own number. Now step to the second row and look only at its second digit. Whatever it is, you write down something different for your second digit. Step to the third row, look at its third digit, choose something different. You keep descending forever, each step taking you one row down and one digit to the right, always choosing to disagree with the digit you find waiting on that diagonal. Now ask yourself where your finished number could possibly live on that list. Could it be the first number? No, because you personally made sure your first digit differs from that one's first digit, so the two numbers part ways immediately. Could it be the 1,000th number? No, because at the 1,000th step you made your 1,000th digit differ from its 1,000th digit. Could it be the trillionth, or the row a billion places down? No, for the same reason. At every single row, you deliberately built in a disagreement at exactly the place that would matter. Your number cannot be any row on the list, because for every row there is a specific digit where you and that row are guaranteed to differ. You have constructed, out of pure stubbornness and a diagonal line, a perfectly ordinary decimal between 0 and 1 that provably is not, and cannot be, anywhere on a list that was supposed to hold every such decimal. The list promised completeness. Your one number is the witness that the promise was a lie. And there is no patching it, because the moment anyone hands you a repaired list with your number squeezed in, you simply walk the new diagonal and build another escapee. The reals cannot be caged. Sit with that for a moment, because it is the discovery that this whole video orbits. For more than 2,000 years, The safest position in mathematics was that infinity was a single vague idea, too slippery even to be a real object, let alone something you could measure. Cantor had now shown not only that infinity is real and measurable, but that there are different sizes of it, and that one specific infinity, the infinity of the smooth continuous line, is provably, demonstrably bigger than the infinity of the counting numbers. We even gave the two sizes names. The size of the counting numbers we call Aleph Null, written with the first letter of the Hebrew alphabet. The size of the real continuum we often call C. And the entire shattering discovery compresses into a single short inequality. Aleph Null is less than C. The first infinity is smaller than the second. There was now a hierarchy where everyone had assumed there could only ever be one floor. And Cantor, having torn that floor open, looked down through it, and what he saw next was somehow stranger still, because most of the numbers on the line, it turned out, were numbers no human being would ever be able to name. Part 7. The Ocean Between the Stars. Before we climb higher, there is one more consequence of the diagonal proof that deserves its own moment, because it is perhaps the most beautiful thing in the entire story. We need to split the real numbers a different way than before. Set aside the divide between fractions and irrationals for a moment, and draw a new line between what mathematicians call the algebraic numbers and the transcendental numbers. The algebraic numbers are the ones that arise as solutions to ordinary equations built from whole numbers. More precisely, a number is algebraic if it is a root of some polynomial equation with integer coefficients, one of those familiar expressions with x and x squared and x cubed and plain numbers, all set equal to 0. That sounds abstract, but the examples are completely familiar. Every fraction is algebraic, because the fraction p over q solves the simple equation q times x minus p equals 0. The square root of 2 is algebraic, because it solves x squared minus 2 equals 0. The cube root of 5 is algebraic. Even the golden ratio is algebraic, since it satisfies a tidy quadratic equation. The algebraic numbers cover essentially all the numbers you ever met in school. Fractions, roots, the solutions of quadratics and cubics, a vast and familiar territory. The transcendental numbers are the outsiders. A transcendental number is one that is not algebraic, one that solves no such polynomial equation with whole number coefficients, no matter how high you let the powers climb or how large you let the coefficients grow. They quite literally transcend the reach of ordinary algebra, which is where the dramatic name comes from. And in Cantor's day, transcendental numbers seemed exotic and rare. It had only recently been proven that a few specific famous numbers were transcendental. The mathematician Charles Hermite proved that the constant E is transcendental in 1873. The mathematician Ferdinand von Lindemann proved that pi is transcendental in 1882, which incidentally settled the ancient puzzle of squaring the circle once and for all. But these were hard-won individual results, single numbers pinned down with great effort, and it was natural to picture the transcendentals as scattered curiosities, strange exceptions dotted thinly among the well-behaved algebraic numbers that made up the real bulk of the line. Cantor turned that entire picture upside down, and he did it almost effortlessly, using the tools he already had. He showed that the algebraic numbers, the whole enormous familiar territory of them, are countable. The reasoning, once you see it, is clean. Each polynomial equation is completely determined by its list of whole number coefficients, and that is just a finite string of integers. But finite strings of integers can themselves be arranged into a single list, exactly the way we listed the fractions. So all the polynomials can be counted, and each individual polynomial has only finitely many roots, only so many solutions. So if you go through the countable list of polynomials, and for each one write down its handful of roots, You sweep up every algebraic number that exists, and the whole collection can be put in a list. The algebraic numbers are countable. They are the same size as the plain counting numbers. Now set that beside what we just proved. The real numbers are uncountable. The algebraic numbers are countable. But every real number is either algebraic or transcendental, with nothing in between. So if the algebraic ones form only a countable collection, a mere aleph null of them, and yet the reals altogether form a vastly larger uncountable infinity, then the transcendental numbers, everything left over once the algebraic ones are removed, must themselves be uncountable. There is no other possibility. The countable algebraic numbers cannot account for the uncountable whole, so the leftovers have to carry the overwhelming bulk. The transcendental numbers do not merely exist, they dominate. They are not the rare exceptions. They are the rule, the ocean, the overwhelming majority of all numbers on the line, while the algebraic numbers we know so well are the vanishing exceptions. Let the strangeness of that sink in by remembering how rare the transcendentals had seemed only a little while before. The first person to prove that any transcendental number existed at all was the mathematician Joseph Liouville, who in the 1840s had to construct one by hand, carefully assembling a special number digit by digit precisely so that it could not satisfy any polynomial equation. It was a delicate, painstaking feat, like building a single artificial creature in a laboratory to prove such a creature could exist. Then came Hermite's proof about the constant E and Lindemann's about pi, each one a major event, each transcendental number a hard-won trophy. The whole atmosphere of the subject suggested that these numbers were freaks, immensely difficult to find, vanishingly rare. A mathematician of the time might have guessed there were only a scattered handful of them in all the reals. And then Cantor, without constructing a single one, proved that they were not the rare exceptions, but the overwhelming majority, that in fact almost every number on the line is transcendental, and the familiar algebraic numbers are the freaks. He did it by a kind of counting argument that names no individual number at all. It is one of the purest examples in mathematics of proving that something must exist, in fact must be everywhere, without ever pointing to a single specific example. Liouville sweated to build one transcendental. Cantor leaned back and proved there were uncountably many, infinitely more of them than all the numbers anyone had ever bothered to name, and he did it almost as a side effect of the diagonal. That contrast, the laborious single example against the effortless, uncountable flood, is one of the most quietly staggering turns in the whole history of the subject. The mathematician E.T. Bell once described this with an image I have never been able to shake, and I want you to let it settle over you slowly, because it is the emotional heart of what Cantor found. The algebraic numbers, Bell said, are like stars scattered against the blackness of the night sky, bright, distinct, nameable points of light. And the transcendental numbers are the darkness itself, the boundless black firmament stretching in every direction in which those few stars are suspended. Think about what that means the next time you imagine the number line as a tidy ruler. Almost every point on it, in a sense that can be made completely precise, is a transcendental number, a number with an endless, patternless decimal that no equation will ever capture, that no formula will ever name, that you could never write down or compute or pin to a page. The numbers we can actually describe, all of them, every fraction and every root and every familiar constant, are the scattered stars. The unimaginable rest, the dark between, is everything else. You live your whole numerical life among a handful of stars and never once touch the darkness that holds them, even though the darkness is almost all there is. And it gets stranger, because Cantor was not finished finding new infinities. He had found one flaw above the counting numbers. Now he asked how many floors there were. The answer turned out to have no end, and one of its questions has no answer at all. Part 8. The ladder with no top. So far, we have found exactly two sizes of infinity. The countable one, aleph null, shared by the counting numbers and the evens and the squares and the integers and the fractions and the algebraic numbers. And the larger one, the size of the continuum, C, the uncountable infinity of the reals and the transcendentals, 2 floors. And the obvious next question, the one Cantor could not help asking, is whether there are more. Does the ladder stop at 2 rungs, or does it keep climbing? Cantor found that it never stops, and the engine that drives it upward is an idea called the power set. Take any collection of things and form a new collection whose members are all the possible subsets of the original, every way of choosing some of the members, including choosing none and choosing all. This new collection of all subsets is the power set. For a small finite collection, you can see the power set is always bigger than the original. A collection of 3 things has a power set of 8 things, because there are 8 different ways to pick a subset of 3 items. 3 becomes 8, and Cantor proved, with another argument in the same family as the diagonal, that this is always true, even for infinite collections. The power set of any collection is strictly larger than the collection itself, always. No exceptions, finite or infinite. Think about what that unleashes. Start with the counting numbers, an infinity of size aleph null. Form its power set, the collection of all its subsets, and you get a strictly larger infinity. Now form the power set of that, and you get one larger still, and the power set of that, larger again. You can keep taking power sets forever, and each one vaults you to a strictly greater size of infinity than the one before. There is no largest infinity. There cannot be, because whatever infinity you propose as the biggest, its power set is bigger. The hierarchy of infinities climbs without end. An infinite ladder of infinities, each rung an entire universe of number larger than everything below it. We label these sizes with the Hebrew letter aleph and a rising index. Aleph null, aleph 1, aleph 2, climbing forever. Cantor had not just found a second floor above the counting numbers. He had found an endless tower, and he was standing at the bottom of it, looking up into a structure with no ceiling. But now a very precise and very natural question arises, and it is the question that would haunt Cantor for the rest of his life. We know aleph null, the size of the counting numbers, is the smallest infinity. We know C, the size of the continuum, is larger. The question is C the very next size up? Is the continuum the immediate successor to the counting numbers, the first floor above aleph null with nothing in between? Or is there some intermediate infinity, some collection larger than the counting numbers, but smaller than the reals, hiding in the gap? Cantor believed there was nothing in between. He believed the continuum was the next infinity after the countable, the very first uncountable size, with no secret floor wedged between them. This belief is called the continuum hypothesis. And try as he might, year after year, Cantor could neither prove it nor disprove it. He was certain it was true. He could not show that it was. The effort consumed him, and the failure wore on him terribly, because it sat at the foundation of the entire world he had discovered, and he could not close it. What happened to the continuum hypothesis in the decades after Cantor is one of the most profound and disturbing results in the history of human thought, and it is worth telling carefully, because it is not a story of someone finally solving the problem. It is a story of discovering that the problem cannot be solved and proving that with certainty. The first half came in 1940 from the logician Kurt Gödel, one of the deepest minds of the 20th century. Gödel showed that the continuum hypothesis can never be disproved using the standard accepted axioms of set theory, the basic rules on which all of this mathematics is built. You will never derive a contradiction by assuming it is true. So far, that sounds like good news for Cantor, as if the hypothesis were safe. But the second half, which arrived more than 20 years later, in 1963, from a mathematician named Paul Cohen, completed the trap. Cohen invented an entirely new and powerful technique called forcing, and he used it to prove the mirror image of Gödel's result. The continuum hypothesis can never be proved using those same standard axioms either. It is worth being clear about how strange and how strong these two results really are, because they are not at all like an ordinary unsolved problem. When mathematicians say a famous conjecture is unsolved, they usually mean that nobody has yet found the proof, that the answer is out there waiting, and we have not been clever enough or lucky enough to reach it. Gödel and Cohen proved something entirely different and far more disturbing. They did not fail to settle the continuum hypothesis. They proved that it cannot be settled, that the standard rules of mathematics are genuinely and permanently silent on the matter. Gödel built a particular mathematical universe, a carefully constructed model of set theory, in which the continuum hypothesis is true and everything stays consistent. Cohen, with his new method of forcing, built a different mathematical universe in which the continuum hypothesis is false and everything also stays consistent. Both universes obey every standard axiom. Both are perfectly legitimate. They simply disagree about whether there is an infinity between the counting numbers and the continuum, and nothing in the rules can break the tie. Think about what forcing actually let Cohen do, because it is almost magical. He found a way to start with a model of mathematics and carefully add new objects to it, new subsets of the counting numbers, like adding new books to a library while guaranteeing the library stays consistent until the continuum grew larger than the hypothesis allows. He could, in effect, dial the size of the continuum to be all sorts of different values, conjuring extra infinities into the gap that Cantor had insisted was empty. The technique was so powerful and so general that it opened an entire industry of similar results, showing that a whole catalogue of natural mathematical questions are likewise undecidable from the standard axioms. The continuum hypothesis was not a lonely exception. It was the first crack that revealed the foundations of mathematics to be riddled with questions that have no answer, true or false statements we have proven we can never decide. Put the two halves together, and you arrive at something that genuinely strains the mind. The continuum hypothesis can be neither proved nor disproved from the accepted foundations of mathematics. It is what logicians call independent of the axioms or undecidable. This is not a statement that we have not yet been clever enough to settle. It is a proof that the question cannot be settled, that our mathematics is simply silent on it, that you can add the hypothesis as a new assumption and get a perfectly consistent mathematics, or add its denial and get a different, equally consistent mathematics, and nothing in the rules will ever tell you which one is correct. Here is a perfectly clear, perfectly precise yes or no question about the structure of number itself. Is there a size of infinity between the counting numbers and the continuum? And the answer is that there is no answer, not because we are ignorant, but because we have proven that the answer is unreachable. Cohen received the Fields Medal, the highest honor in mathematics, for this work in 1966. And the universe of number that Cantor opened turned out to contain, right near its foundation, a door that is provably locked, with the key provably destroyed. We do not know whether infinity has a flaw between its first two stories. We know that we cannot know, and the man who first asked the question did not live to see even half of that answer. He lived only the part that broke him. Part 9. The price of seeing too far. It would be a kind of dishonesty to tell you all of this as a clean parade of triumphs, because for Georg Cantor it was nothing of the kind. The ideas we have been turning over with such pleasure, the pairing of the evens, the diagonal, the endless ladder, were not received in his lifetime as the glories they are. They were received, in many quarters, as scandals, and the cost of having seen them fell on one man, almost alone, and it was a heavy one. The fiercest of his opponents was the man we met earlier, his former teacher, Leopold Kronecker, who held great power in the mathematical establishment of Berlin. Kronecker was what is called a finitist. He believed, deeply and on principle, that mathematics should concern itself only with the finite, that the whole numbers were the solid bedrock of everything, and that Cantor's completed infinities were not just unnecessary, but actively diseased, a kind of nonsense that threatened to corrupt the foundations of the subject. There is a famous line attributed to Kronecker that captures his whole philosophy. God made the integers, he is supposed to have said, and all else is the work of man. To a man who felt that way, Cantor's tower of transfinite infinities was not a discovery. It was a contamination, and Kronecker did not confine his disapproval to private opinion. He used his influence against Cantor with real force. He worked to block the publication of Cantor's papers. He is reported to have called Cantor a corrupter of youth, a charge with an ugly weight to it. And crucially, Cantor longed throughout his career for a position at one of the great Berlin institutions, a recognition his work surely merited, and Kronecker stood in the way, blocking the path to the appointment Cantor wanted most. Cantor remained at Halle, in the smaller world, and he believed, with good reason, that a powerful man was deliberately holding him down. Not everyone turned away. The mathematician, Richard Dedekind, himself a profound thinker about the foundations of number, understood the depth of what Cantor was doing and corresponded with him and encouraged him. That support mattered. But it could not undo the larger isolation, the sense of fighting for ideas that the most influential figures in his field regarded as madness. And from around 1884, something in Cantor began to give way. He suffered the first of what would become a recurring series of episodes of deep depression, periods of profound darkness that would return again and again for the rest of his life. Modern scholars, looking back at the pattern of his illness, think it very likely that he suffered from what we would now call bipolar disorder, the long swings between elevated, intensely productive states and crushing lows, though of course no such diagnosis existed to be offered to him at the time. He spent stretches of his later years in a sanatorium, sometimes returning to mathematics with bursts of energy, sometimes turning away from it entirely toward other obsessions. The man who had given the human race a map of the infinite was, for long periods, unable to find his own footing. His final years were genuinely bleak. The First World War had come, and Germany was gripped by hardship and hunger, and conditions even in institutions were grim. In 1917, against his own wishes, his family had him admitted once more to the sanatorium at Halle, the city where he had spent his whole career. And it was there, on the 6th of January 1918, that Georg Cantor died, in that sanatorium, far from the great centres he had hoped to join. Having spent his last years in illness and relative neglect, he was 72 years old. He had looked further into the nature of infinity than any human being before him, and he died in a small room, in a starving country, his greatest questions still open. Try, for a moment, to actually picture those last years, because the contrast is almost too sharp to hold. Here is a man whose mind had ranged across infinities without number, who had climbed a ladder of ever greater endlessness that has no top, who had held the whole transfinite tower in his imagination and given it a language. And here is where that man spent his final stretch of life. A quiet room in a sanatorium in Halle, in the middle of the First World War, in a country worn thin by years of fighting, where even the institutions meant to care for the ill were short of food and short of comfort. The boundlessness he had discovered, and the small bare walls around him, could hardly have been further apart. He had been admitted in 1917 against his own wishes. His thoughts, in his well periods, still turned to the questions that had always held him, the continuum hypothesis still open, still unanswered, still refusing him after a lifetime of effort. And in his dark periods, the depression that had shadowed him for more than 30 years closed back in. On the 6th of January, 1918, it ended. Georg Cantor died in that room, 72 years old, far from Berlin, far from the recognition he had spent his life hoping for, his greatest question still unresolved and, though he could not have known it, soon to be proven unresolvable. There is a particular kind of sorrow in that, in a life given over to mapping the infinite ending in such a small and finite confinement, in a man who had expanded what the human race could think, dying half forgotten, in a time when the world was busy tearing itself apart. He had been right about everything that mattered in his mathematics, and it brought him, in his own lifetime, more grief than glory. And here is the part that I find almost unbearable in its timing. Cantor's vindication had, in fact, already begun, even if he was in no condition to feel its full warmth. The generation of mathematicians coming up behind him increasingly understood that he had not corrupted mathematics. He had expanded it. He had handed it a new continent. The towering mathematician David Hilbert, one of the most important figures of the age, became one of Cantor's great champions, and he gave that defense a form that has never been forgotten. No one, Hilbert declared, shall expel us from the paradise that Cantor has created for us. A paradise, not a contamination, not a disease, not the ravings of a corrupter of youth, but a paradise, a new and beautiful world that mathematics would refuse to give up. That is the verdict history rendered, and it is the one that stands today. Cantor was right. The mathematics was sound. The infinities are real, and they come in different sizes, and the proofs are airtight. But the man who saw it first paid for the seeing with his peace and much of his happiness, and he was gone before the paradise he built was fully recognized as his. There is a lesson in that about the price of being early, about the loneliness of carrying a true thing through a world that is not ready for it. And there is one more turn left in this story, because the infinity Cantor mapped in the abstract did not stay politely inside mathematics. It walked straight into physics, into the equations we use to describe the real universe, and there it has caused a kind of trouble that is still not resolved tonight. Part 10. When Infinity Walks into Physics. It would be comforting to think that all of this strangeness is safely quarantined inside pure mathematics, a beautiful game played with symbols, with no bearing on the solid physical world you actually live in. But that comfort is not available, and this is where the title of tonight's journey earns itself, because infinity does not stay in the mathematician's paradise. It shows up, again and again, uninvited, right in the middle of physics, inside the equations we trust to describe reality, and when it appears, physicists do not celebrate, they wince. Because in physics, an infinity is very often a sign that something has gone wrong. Consider the most dramatic example, the one at the heart of a black hole. When you take Einstein's theory of general relativity, our deepest and most successful description of gravity, space, and time, and you follow its equations down into the center of a black hole, the numbers do something alarming. The density of matter climbs toward infinity. The curvature of space-time climbs toward infinity. The equations are describing a point of infinite compression, a place where everything we can measure shoots off the top of the scale and becomes unbounded. This point is called a singularity. And the same thing happens if you run the history of the entire universe backward in time toward its beginning. Wind the expansion of the cosmos back far enough, and general relativity again predicts a singularity, a first instant of infinite density and infinite curvature, the so-called Big Bang singularity. Now, here is the crucial thing about how physicists read these infinities. Most of them do not believe the infinities are real. They do not think there is genuinely a point of literally infinite density sitting at the center of every black hole. Instead, they read the appearance of infinity as a warning light, a signal that the theory has been pushed past the limits of where it works, that general relativity is breaking down, and that some deeper theory, one we do not yet have, is needed to describe what truly happens there. The infinity is not the answer. It is the theory's way of confessing that it has run out of road. This pattern repeats in the other great pillar of modern physics, quantum field theory, which describes the behavior of particles and forces at the smallest scales. When physicists first tried to calculate certain basic quantities using this theory, things like the properties of an electron, the calculations kept returning infinite answers. Not large numbers, infinite ones. These infinities arose, in part, from treating particles as perfect points with no size at all, which forces you to consider what happens at infinitely small distances, and the mathematics blows up. For a while, this threatened to sink the entire theory, because a physics that predicts infinite answers predicts nothing useful at all. The escape came through a technique called renormalization, which is, in essence, a systematic and very carefully justified procedure for subtracting the infinities away, for absorbing them into the definitions of measured quantities like mass and charge, leaving behind finite answers. And here is the astonishing thing. It works. Renormalization produces some of the most accurate predictions in all of science, agreeing with experiment to a staggering number of decimal places. And yet many physicists have always felt a deep unease about it, including some of its own architects, who regarded the need to sweep infinities under the rug, however rigorously, as a sign that the theory, for all its triumphs, was conceptually unfinished. When physicists later tried to apply the same quantum techniques to gravity itself, the infinities came back in a form that renormalization could not tame at all, and that failure is one of the central reasons we still do not have a complete theory of quantum gravity tonight. The unease about renormalization is worth lingering on, because it was felt most sharply by the very people who were best at using it. Paul Dirac, one of the founders of quantum theory and one of the most precise minds the field has ever produced, never made peace with it. He complained, late in his life, that the whole procedure of subtracting infinities was not sensible mathematics, that sensible mathematics involves neglecting a quantity when it is small, not neglecting it because it is infinitely large and you do not want it. He suspected that the need to renormalize meant the theory was not finished, that some better formulation, free of the infinities, was still waiting to be found. And he held this view while fully acknowledging that the theory's finite predictions were spectacularly, almost miraculously accurate. That is the strange double character of infinity in physics. It is woven into our most successful theory of matter, and that theory predicts reality to a precision unmatched anywhere in science, and yet the infinity at its heart is treated by many of its own masters as a symptom rather than a truth, a thing to be managed and subtracted, a placeholder for understanding we do not yet have. When physicists carried these same methods to gravity, hoping to build a quantum theory of space-time itself, the infinities returned in a far more vicious form. In quantum field theory, you can absorb the infinities into a small handful of measured quantities and move on. But in quantum gravity, the infinities multiply without limit, demanding an endless number of corrections, an infinity of adjustments to chase, an infinity of divergences, and the subtraction trick simply fails. This is one of the deepest reasons we still have no accepted theory uniting gravity with the quantum world, no settled account of what actually happens at the singularity inside a black hole, or at the first instant of the universe. The infinities that general relativity and quantum mechanics each generate, when forced together, refuse to be tamed. The two greatest theories in physics meet, and where they meet, infinity blooms uncontrollably and tells us our understanding has run out. But infinity is not only a troublemaker in physics. Sometimes it is woven right into the working machinery, accepted and used. The whole framework of quantum mechanics is built on a mathematical structure called a Hilbert space, named for the same David Hilbert who defended Cantor's paradise. And that space, the arena in which a quantum state lives, is generally infinite dimensional. The infinite is not an embarrassment there. It is part of the load-bearing structure. And Hilbert himself, to help people grasp the strangeness of Cantor's actual infinite, invented a famous parable in his lectures in the 1920s, the story of an infinite hotel. Imagine a hotel with infinitely many rooms, every one of them occupied. In a finite hotel, full means full, and a new guest must be turned away. But in the infinite hotel, when a new guest arrives, the manager simply asks every guest to move to the next room along, the guest in room 1 to room 2, room 2 to room 3, and so on forever. Every guest still has a room, no one is left without, and yet room 1 is now empty for the newcomer. The full hotel had room for one more. It is exactly the even numbers trick from the very start of our journey, the part being the size of the whole, dressed up in beds and corridors. And in 2015, physicists actually built a working physical version of Hilbert's hotel using beams of light, manipulating an infinite ladder of quantum states to shift them all and open up infinitely many empty levels, turning Cantor's century-old paradox into something you could do on an optical table. Cantor's infinities, it turns out, are not just abstractions. They are wired into the deepest physics we have, which raises the most concrete and most haunting question of all. Is there actually an infinity out there, in the real universe, beyond the equations entirely? Is space itself endless? And the honest answer is one of the strangest things I will tell you tonight. Part 11. The Edge That May Not Exist. When you look up at the night sky, it is natural to assume the universe simply goes on forever. Endless space, endless stars, no wall, no edge, no end. But that assumption is far harder to justify than it sounds, and modern cosmology has spent a great deal of effort trying to pin down whether the universe is actually infinite or merely very, very large. The answer we have arrived at is delicate, and it depends on something you might not expect: the shape of space itself. The geometry of the universe can, in principle, take one of a few broad forms. It could be curved, like the surface of a sphere, closing back on itself, which would make it finite. It could be curved the other way, like a saddle opening outward. Or it could be flat, in the precise geometric sense that the rules of ordinary school geometry hold across the largest scales, parallel lines staying parallel, the angles of a triangle adding to exactly the familiar amount. And we can actually measure which it is, chiefly by studying the faint afterglow of the early universe, the cosmic microwave background, with instruments like the Planck satellite. The verdict of those measurements is striking. The universe appears to be flat, and not approximately flat, but flat to within a tiny fraction of a percent, as far as we can detect, perfectly flat. And in the simplest interpretation, a flat universe is a spatially infinite one. It extends without end in every direction, an actual physical infinity of space, stretching on forever beyond anything we can ever see. I have to be careful and honest here, because the link is not airtight. A flat geometry does not strictly force an infinite universe. It is possible, in principle, for space to be flat and yet finite if it has an unusual closed-up topology, the way the flat surface of a video game screen can wrap around, so that leaving one edge brings you back at the other, finite in extent, yet flat in geometry, like the surface of a donut. So flatness makes infinity natural and likely, but not certain. When cosmologists try to put numbers on the question, gathering all the evidence, the estimates for the probability that space is genuinely infinite come out somewhere in the rough range of 2/3 to nearly all but certain, depending on the assumptions you start with. In other words, our best current reading of the universe says it is probably infinite, but leaves the door open. Notice, too, the crucial distinction that often gets blurred. The observable universe, the part we can actually see, is definitely finite. It is about 93 billion light-years across. But it is finite only because the universe has a finite age, around 13.8 billion years, and light has only had that long to travel to us. The edge of the observable universe is not an edge of space. It is just the distance beyond which light has not yet had time to reach us. The actual universe almost certainly continues far past it, and may continue without end. It is worth pausing on just how carefully that flatness has been measured, because it is one of the quiet triumphs of modern cosmology. When light left the early universe, not quite 400,000 years after the beginning, it imprinted a pattern of faint, hot, and cold spots across the sky, a pattern we can still see today in the cosmic microwave background. The typical size of those spots depends on the geometry of the space the light traveled through to reach us. If space were curved like a sphere, the spots would look slightly magnified. If it were curved like a saddle, slightly shrunken. By measuring the spots with great precision, cosmologists can read off the curvature of the universe the way you might infer the shape of a lens from how it bends an image. And the answer that comes back, again and again, is that the spots are just the size that flat space predicts, with no detectable curvature at all, to within a fraction of a percent. As far as our finest instruments can tell, the universe is flat. Not curved so gently, we cannot yet see it, though that remains possible, but flat to the limits of measurement. That single, measured fact carries the staggering implication. Flat space, in the simplest reading, is infinite space. So, our best current map of the cosmos points, gently but persistently, toward a universe that does not end, that has no boundary, no outer wall, no edge, anywhere, but continues on past the horizon of what we can see, on past the farthest galaxy, on without limit in every direction. We cannot prove it because the finite but flat possibility lingers, and because we can only ever measure the patch we can see. But the most natural interpretation of the data we actually have is that you are sitting inside an infinity right now, a genuine physical endlessness, and that the only thing stopping you from seeing it is the youth of the universe and the finite speed of light. And if space truly is infinite, a consequence follows that is so strange it sounds like science fiction, yet it falls straight out of simple logic. In any finite region of space, there are only finitely many ways that matter can be arranged, only so many configurations of particles, vast but finite. But an infinite universe contains infinitely many regions the size of our observable patch. And if you have infinitely many regions, each able to take only finitely many possible arrangements, then arrangements must eventually repeat. Somewhere out there, unimaginably far away but real, there would be a region identical to this one. A copy of this galaxy, this world, this room. A copy of you reading these words, with every atom in the same place. Not one copy, but infinitely many, scattered through the endless dark, some identical and some differing by a single thought. This is sometimes called the cosmological doppelganger, and it is not mysticism. It is the direct, sober consequence of taking an infinite space seriously. Run the logic a little further, and it grows stranger still. If the configurations repeat, then there is not just one distant copy of this room, but an endless supply of them, and among that endless supply, every possible variation on your life is playing out somewhere. A version where you made the opposite choice this morning. A version where a single atom landed differently and nothing else changed. A version identical to you in every respect up to this exact instant, who will read the next sentence and then do something you will not. None of this requires any new physics. It requires only that space be truly infinite and that the laws be the same everywhere. And from those two modest assumptions, the endless copies follow as surely as 2 and 2. The abstract infinities Cantor pulled out of the counting numbers would, in this picture, have a literal address in the sky, written in stars and worlds and other versions of your own life, which makes it matter enormously, more than any abstract question should, whether infinity is truly out there or whether it is only ever a tool in our minds. And that, remarkably, is exactly the fight some of the sharpest physicists alive are having right now. Part 12. The Quiet Revolt Against Infinity. For all that infinity has done for mathematics, and for all the ways it threads through our physics, there is a growing unease among some physicists that infinity may be less a profound truth about the universe and more a beautiful mistake we keep making. A quiet revolt has been building, and one of its most visible voices is the physicist Max Tegmark, who has argued, bluntly, that infinity may be the assumption that is quietly ruining physics. It is a striking claim from someone working at the center of modern cosmology, and the argument behind it is worth taking seriously because it is not the complaint of someone who finds infinity too hard. It is the complaint of someone who finds it too convenient. The core of the argument is disarmingly simple. We have never measured an infinite quantity, not once. No one has ever measured an infinite distance, an infinite density, an infinite temperature, an infinite anything. Every measurement any instrument has ever returned in the entire history of science has been a finite number. Infinity never shows up in the data. It only ever shows up in the theory as an idealization, an assumption we put in by hand because it makes the mathematics smoother, or because we cannot imagine where space would stop. And here is Tegmark's sharpest observation. The places where infinity appears in our theories are precisely the places where those theories stop working. The singularity in the black hole, where the equations break down, the infinite integrals of quantum field theory, which we have to renormalize away, and a particularly nasty problem in cosmology called the measure problem, which arises in theories where the universe spawns infinitely many regions or infinitely many outcomes. When everything that can happen happens infinitely often, you lose the ability to say that anything is more likely than anything else, and probability, the bedrock of how we test theories against reality, quietly stops making sense. Infinity, in other words, does not tend to mark the spots where our theories triumph. It tends to mark the spots where they fall silent. There is a further point that gives the argument real teeth. When physicists run their most sophisticated simulations of the universe, modeling the formation of galaxies, the behavior of matter, the unfolding of cosmic structure, they do it with finite computers, using finite resources, treating everything as finite. And those finite models work magnificently. They reproduce the universe we see, without ever needing a single, genuine infinity anywhere inside them. So, Tegmark and others ask a pointed question. If we can describe everything we actually observe using only finite quantities, and if the only places infinity ever appears are the places our theories collapse, then why are we so sure infinity is real? Perhaps, they suggest, the right move is the radical one, to retire the infinite altogether, to stop assuming that space is an infinitely divisible, infinitely extended continuum, and to treat the physical world as finite through and through. If you do that, some of the deepest headaches in modern physics, including the measure problem and the runaway infinities of inflationary cosmology, simply dissolve because the infinity that created them was never there to begin with. The measure problem deserves a closer look, because it is the sharpest example of infinity not as a harmless idealization, but as an active wrecker of our ability to do science. Many modern theories of the early universe involve a process called inflation, a brief episode of staggeringly fast expansion just after the beginning, And in many versions, inflation does not happen just once. It happens eternally, spawning new regions, new bubble universes, endlessly, forever. That sounds grand, and it may even be true, but it carries a hidden poison. If the process produces infinitely many regions of every kind, infinitely many where the constants of physics come out one way, and infinitely many where they come out another, then when you try to ask a simple question, such as how likely is a universe like ours, you are forced to compare one infinity against another. And comparing infinities, as Cantor taught us, is treacherous. Without some rule for how to weigh them, every outcome happens infinitely often, and infinity divided by infinity gives you no answer at all. Probability, the very tool we use to test a theory against observation, quietly dissolves. The theory predicts everything, which is to say it predicts nothing, and we lose our grip on how to check it. That is the heart of Tegmark's complaint. Infinity, in these cases, is not adding richness to physics. It is dissolving the floor we stand on to do physics in the first place. And his proposed cure is the radical one: to deny that the relevant infinities are real, to insist that space is finite, that the number of regions is finite, that there is no actual infinite continuum underneath any of it, and to watch the paradoxes evaporate as a result. There is a long shadow of history here as well. In the foundations of mathematics, there has always been a small, stubborn school of thinkers called finitists, and an even more radical group called ultrafinitists, who deny that the natural numbers truly go on forever, who hold that there is, in some real sense, a largest meaningful number, that the endless line we have been walking is itself a fiction. They have always been a tiny minority, easy to dismiss. But Tegmark's physical proposal is their mirror image, the same suspicion arriving from the side of physics rather than logic, and it makes the old finitist position suddenly look less like a quaint stubbornness and more like a live possibility about the actual world. This is not the majority view, and it is not settled, and there are serious physicists who think the infinite continuum is perfectly fine and see no reason to abandon something that has served so well. But the fact that the debate is live at all is the point I want to leave you with. There is a deep irony folded into it, and it brings our whole story full circle. Cantor's great antagonist, Leopold Kronecker, the finitist who fought him so bitterly, who insisted that only the finite was truly real and that the completed infinite was a kind of illusion, was dismissed in his own time as a reactionary standing in the way of progress. And now, more than a century later, a strand of cutting-edge theoretical physics is circling back towards something that rhymes with his old suspicion, wondering aloud whether the infinite belongs in our description of nature at all. The mathematics of infinity stands as firm as ever. Cantor's proofs are not in question. But whether that magnificent mathematics describes the actual universe, or whether it is a tool of breathtaking beauty that we have mistaken for a feature of reality, is a question that is genuinely open tonight, argued in journals and seminar rooms by people who do this for a living. And that leaves us, at the end of all this, with a final truth about infinity that is stranger and quieter than any single result along the way. Part 13. Infinity has laws. We began with a child's game. Write the numbers, cross out the odds, count what remains. And we followed that game off the edge of the familiar world, into a place where a part can be exactly as large as the whole, where the dense crowd of fractions is no bigger than the lonely counting numbers, where a single line segment holds as many points as the entire endless line, where almost every number is one no human will ever name, and where the floors of infinity rise in an endless tower with no ceiling anywhere above. At the start of this journey, you almost certainly believed that infinity was simply a word for something very, very large, a vague gesture toward the boundless. I hope that by now that idea has quietly dissolved, and something more precise and more unsettling has taken its place. Because here is the thing that I find genuinely beautiful and genuinely disturbing about everything we have seen. The terror of infinity is not that it is formless or chaotic or beyond all reason. It is exactly the opposite. Infinity has laws, strict ones. You can prove, with the same certainty you can prove, that 2 and 2 make 4, that the even numbers are the same size as the counting numbers, that the reals are larger than both, that the transcendentals drown the algebraic numbers, that no infinity is the largest. These are not opinions or impressions or poetic flourishes. They are theorems, locked down by airtight argument, as solid as anything in human knowledge. The infinite, which Aristotle and Gauss said could never be a real object of study, turned out to be one of the most lawful, most rigorously governed territories the human mind has ever mapped. Infinity has laws. That was the promise at the start, and it has been kept in full. And yet, the two deepest questions we know how to ask about infinity have no answers we can reach. Within mathematics, the continuum hypothesis, the simple question of whether there is a size of infinity between the counting numbers and the continuum, has been proven undecidable, a clear yes or no question that our mathematics can neither confirm nor deny, a locked door with the key destroyed. And within physics, the even simpler question of whether infinity is actually real, whether the space you are sitting in goes on forever, whether there is genuinely an infinite anything anywhere in the universe, remains genuinely open, with brilliant people arguing both sides tonight. So the final law of infinity, the deepest one, is the strangest of all. Infinity is lawful, precise, and rigorous, and still it slips through our fingers at the exact moment we ask whether it is real. We have mapped it more carefully than we have mapped almost anything, and we still cannot tell you whether it exists outside our own minds. Think back, now, to where we started, to that child's game with the numbers from 1 to 10. You crossed out the odds, and you were left with half, and it seemed like the most ordinary thing in the world. The whole was greater than the part, exactly as Euclid wrote down more than 2,000 years ago, exactly as you have believed your entire life. And then we refused to stop, and we followed that one small refusal all the way to here, to a place where that ancient certainty lies in pieces. The whole is not always greater than the part. A line segment is not smaller than the line. The fractions are not more numerous than the counting numbers. Most numbers cannot be named. The infinities rise in a tower without a top. And the two simplest questions left standing, whether there is an infinity between the first two, and whether any of this infinity is real, are questions we have either proven unanswerable or cannot answer yet. Every step along the way was forced by nothing more than honest reasoning, each one following from the last, and yet the destination is a country where almost nothing your intuition packed for the journey still works. That, I think, is the real meaning of the strange phrase we began with, that infinity has laws. We tend to fear the infinite because we imagine it as formlessness, as chaos, as the place where all rules dissolve. The truth turned out to be the exact opposite, and it is far more unsettling. The infinite is not lawless. It is overwhelmingly, rigorously lawful. It obeys theorems as strict and as certain as anything in mathematics. You cannot do whatever you like with it. It tells you, with complete authority, that the evens equal the counting numbers, and the reals exceed them, and no size is the largest, and you do not get a vote. The terror was never that infinity has no rules. The terror is that it has rules, ironclad ones, and they are not our rules, and they do not bend to our intuitions, and at the very deepest level, they refuse to tell us the one thing we most want to know, which is whether the whole magnificent structure describes the universe we live in, or only the inside of our own minds. Georg Cantor, who saw further into this than anyone before him, and paid for the seeing, never stopped believing in what he had found. even when the most powerful men in his field called it madness, and his own mind turned against him. Near the end, he wrote words I want to leave you with, because they belong to him and not to me. My theory stands as firm as a rock, he said. Every arrow directed against it will return quickly to its archer. How do I know this? Because I have studied it from all sides for many years, because I have examined all objections which have ever been made against the infinite numbers, and above all, because I have followed its roots, so to speak, to the first infallible cause of all created things. He was right about the mathematics. It did stand as firm as a rock, and it stands there still, a paradise no one has been expelled from. Whether the universe itself is built on that same rock, or whether infinity is the most beautiful tool we ever mistook for the truth, is the question you can carry with you now, out past the edge of the counting numbers, into the dark between the stars, where the evens and the odds and the endless line go on and quietly on.